You type a few words into an AI, and a perfectly coherent sentence comes out. It really feels like magic, right? But what's actually going on under the hood? Well, today, we're going to pull back the curtain. We're going to follow a single piece of information, what's called a token, on its incredible journey from your prompt deep into the machine and back out again as the next word. Let's get started.
Okay, first things first, let's get one major misconception out of the way with this quote. We tend to think of AIs as knowing stuff, like they're just pulling facts out of some giant encyclopedia. But that's not what's happening at all. Inference, that's the process of generating new text, is really just a sequence of probabilistic geometric decisions. It's all just math and geometry, really. And if you can wrap your head around that one idea, everything else we're about to talk about will click into place.
So, to make this whole thing easy to follow, we've broken our token's journey down into a simple three-act play. First, we see how our human language gets translated into pure math. Then, we follow it as it travels through this wild world of math. And finally, we'll see how it transforms back into language. Pretty straightforward, right? Let's dive into Act 1.
All right, Act 1. Language becomes math. This is the first and maybe the most crucial hurdle. How does a machine take our words, all their nuance, their messiness, their meaning, and turn them into something it can actually work with? The answer is numbers.
So, the first thing you need to know is that the model doesn't actually see words. It sees things called tokens. The very first step is called tokenization. So let's say your prompt is, "the storm is." The model chops that up into these little pieces, the tokens. Then it gives each token a unique ID number. It's kind of like a secret code or a catalog number for every possible piece of language it knows.
But a simple ID number isn't very useful on its own. So what happens next? Well, that number acts like an address. It tells the model to go to a massive lookup table, called an embedding matrix, and find the matching row. And that row? That's the magic. It's a vector, basically a long list of numbers. You can think of this vector as a coordinate, placing our token at a very specific spot on a huge multi-dimensional map of meaning. And just like that, our language is now officially the native language of the machine, math.
And now we enter Act 2, the world of math. Our token, which is now a vector, a point on a map, is ready for the main event. It's about to dive into the heart of the model, the transformer layers. This is a whole stack of complex mathematical machinery. Its job? To take our token and give it context by looking at everything around it. Seriously, this is where all the cool stuff happens.
You can think of each one of these layers as a two-part machine. Our token has to pass through both parts. The first is called self-attention. That's where it figures out its relationship to other tokens. And the second part is the feed-forward network, which kind of thinks about those relationships. Our little token is going to do this two-step dance over and over again through dozens of layers.
So let's break down that first step, self-attention. What is that? Honestly, the best way to think about it is like a cocktail party for tokens. Our token gets to look around the room at the and storm and essentially ask, hey, how important are you to me in this specific sentence? It's all about figuring out who to pay attention to. This is how the model starts to build up a picture of the context.
Okay, so how does this cocktail party actually work? Well, to make it happen, every single token creates 3 new specialized vectors for 3 different jobs. First, there's the query vector. Think of this as the token's question, what am I looking for? Then, every other token has a key vector, which is like its name tag, saying, here's what I am. And finally, there's the value vector, which is what the token actually brings to the conversation. Here's the useful info I've got.
And this is where that whole geometric decisions thing comes into play. It's basically a relevance tournament. Our token sends out its query vector, its question. Then the model compares that query to every other token's key vector, their name tag. Geometrically, it's just checking how much the vectors are pointing in the same direction. If they're aligned, they get a high score. If they're not, low score. This creates a score for how relevant every token is to every other token. Now, those raw scores get turned into simple percentages. And check this out. For our token the model has decided, mathematically, to pay a whopping 80% of its attention to the word storm. It pays a little attention to itself and almost none to thee. It has figured out, just through geometry, that in the phrase, "the storm is," the word storm is the absolute key piece of context. And here's a really important detail. The model doesn't just throw away the original meaning of is and replace it. Nope, it takes all that juicy context it just gathered, mostly from Storm, and it adds it to the original vector for is. This is a trick called a residual connection. It means the token gets to learn from its neighbors and evolve, but it never forgets its own identity. It keeps its core, but it gains context.
Okay, so that was part one of the machine. Now for part two. If self-attention was about asking, who should I listen to, the feed-forward network is about asking, okay, now what do I do with all that information? This is where the model gets to, well, for lack of a better word, think. It processes all that new context it just absorbed, looking for important patterns and features to pass along to the next layer.
So picture this. Our token goes through this two-step process, attention, then feed forward. Not just once, but dozens and dozens of times, layer after layer. And with each pass, its vector gets a little smarter, a little more refined, a little more context-aware. By the time it pops out of the final layer, it's not just the vector for the word is anymore. Oh no, it has become this incredibly rich, distilled mathematical summary of the entire prompt.
And that brings us to the grand finale. Act 3. Where math becomes language. Our token has survived its epic journey through the mathematical wilderness. Now the model has one last job to do. Translate that super smart, context-packed vector back into something we can understand. A word.
So how on earth does it do that? It takes that final vector and multiplies it by another gigantic matrix. And what this does is produce a raw score called a logit for every single word the model knows. We're talking tens of thousands of scores. Now these aren't probabilities just yet. Think of them more like a raw gut feeling score for how plausible each word would be as the next word in the sentence.
You can really think of this as the final vote. That final vector is pointing to a very specific spot on the map of meaning, and it projects that meaning out across the entire vocabulary. Words that are nearby on the map, words that make sense, like coming or over, they get a high score. And words that are on the other side of the map, total nonsense words like banana, get a super low score.
And for the final step, those raw logit scores are converted into an actual probability distribution. And this is what you get. The model doesn't just spit out one answer. It creates a forecast. It says, okay, there's a 45% chance the next word is coming, a 25% chance it's approaching, and so on. From there, it just picks one based on those odds. It's literally rolling the dice, but the dice are heavily weighted towards the most likely outcomes.
Which leads us to this, just a perfect way to summarize everything. An AI isn't a warehouse full of sentences it just looks up. It's a landscape, a vast, complex landscape of meaning that was sculpted during its training. Your prompt is like dropping a pin at a starting location on that map. And all the model is doing is calculating the most probable path to take from there.
So let's quickly recap the entire trip. Step 1. Language becomes math. Your text gets tokenized and turned into a starting vector. Step 2. The journey through math. That vector travels through layer after layer, using attention to find relationships and a feed-forward network to think about them. And Step 3. Math becomes language again. The final super smart vector votes on every word in the dictionary, probabilities are created, and a new token is born.
So that leaves us with the big question, doesn't it? When an AI gives you an answer that seems incredibly insightful or creative, is it actually reasoning, or are you just watching a master surfer navigate a vast, complex landscape of probability? A landscape that was shaped entirely by the geometry of our own language. It's definitely something to think about.